Hi, everybody. My name is Sebastian, and a master degree student at the Civil and Environmental Engineering Department in the University of Maine, and my advisors are Professor Aaron Galland and Bill Davis. Today, I'm going to present a little part of a research we are undergoing related to the behavior of integral abutment ridges supported on micropiles. And this still part focuses on what's the flexural strength of the thread connection. So what's the problem statement? Let's look at here. Now we have that shallow bore oxides that are kind of common in Maine. It's pretty hard to drive common pile like H pile section to the desired depth. So in this case, micropile are pretty suitable since they can be drilled through the rock and then achieve the desired depth. But due to the inner nature of integral abutment bridges, uh, all the thermal and shrinkage deformations that are undergoing by the superstructure are transmitted to the foundation, and thus the micropile must be designed to hold axial but also lateral loading. And it happens that the thread connections of these micropiles represent a source of structural weakness, uh, being possible that they present early failure and thus losing all its lateral loading capacity. Now, it happens that at today, there's certainly no way to predict what the threaded joint structural strength is, and that's desirable during the design process. So we have been focusing on that during a couple of weeks, and that's what I'm going to present today. So when we go to literature, there's essentially two failure modes of these joints. They can fail due to jump out, or well, due to rupture. Now, jump out is a kind of career failure mode on which there's no damage. Essentially, threads are perfectly okay, both ends of the connection are okay, but still the threads just ride one over the other, disconnecting the two sections of the pile. While the rupture is just happened that it was still connect, but the material reaches its ultimate tensile stress and then just breaks. Now, I say in the literature there's no validated methodology, but certainly it is. Musselman present in 2007 a methodology based on several hypotheses. So first of all, they say that during bending, well, we know we have compression and tensile stresses, but in the tensile side, when we look at the threads, that the one of the face of the threads is still in contact while the other one is losing the contact. And that makes that this side of the section, I mean, all the tension side of the cross section is not field effective. And the way to count that is just to reduce the thickness of the tube or pipe to a level below the threads. Second hypothesis was that during their testing, they observed kind of curious distribution of strains. They found out that the strains were linear in compression as usual, but they rapidly increased from the neutral axis position to a certain value, and then they got pretty constant in the wall tensile side. And that will, based on a constitutive relationship for the material in this case, still will translate more or less in a linear compression, linear distribution for compressive stresses and basically constant tensile stresses. So in this methodology, we can find out what the bending capacity or moment capacity corresponds to each failure mode. If we set up this tensile stress here as the rupture stress or as the jump out stress. And we can solve what the compressive stress must be to accomplish equilibrium, and that is the tensile stress resultant equals the compressive stress resultant. Now, there are several questions here that remain unanswered. First, what's the limiting stress? We have more or less some certainty based on material testing, what the rupture stress, but what about jump out stress? And so we have some hints from the oil and gas extraction industry. They have developed some theory back in the 60s that tell us what the jump out stress or load, but under pure tension leveling. And the question is, would be the same for bending? So that's some questions that remain unanswered. And also, what are the mechanics behind this strain distribution? So those questions remain still unanswered, so that makes the methodology lose some validity or makes them questionable. But still, we can try to validate that methodology by comparing predictions by means of these hypotheses with actual measurements. So Musselman did something like that in the past. The range of material and geometric properties and thread shape and size was so narrow that still we can cast doubts on the validity of this methodology. So that's what we did during some time, and we look at the literature, several studies reporting field and laboratory testing of micropilot thread connections, and and I found out essentially three types of connections. Two of them are reports from studies at Europe, while the other one report the studies in the United States. So the Europe type connection are like a male-female connection with square shaped threads, different diameter and thread size. And also we have this male-to-male connection with an external box holding both of them together. And in the case of the US type, we have this male-to-female connection, but the threads are B-shaped or triangular shape. And then we got 47 tests, uh, including some field testing and diameters ranging 88 millimeters to 273 millimeters. That's more or less the commercial range of uh, pipes diameters that we can apply. and and the results date. So in the figure, we have what the observing moment capacity was, and in the vertical axis, we have our predictions through this methodology, and we have symbols for every connection type, the Europe type, the US type, and we are differentiating also what of the what are field testing and laboratory testing. And we find out pretty good agreement. So something that is nice in the figure that we have the one-to-one slope line, that will be perfect agreement, and the dots are in the case of the Europe type testing are almost in perfect agreement, while we have some scatter for the US type, but still in average they are falling over the line. We are also able to predict the failure mode. All of these USI tests failed due to jump out, and that was predicted by the methodology, and all of the Europe type failed due to rupture, and we also predict that. Something to keep in mind here is that this field testing has probably the biggest scattering here. That's because there are too many uncertainties with field testing. So there is certainly no safe way to directly measure moments at the connection. So what we could extract from the literature were finite element analysis of the same test. And while because displacements were in pretty good agreement between the model and the measurement, we can believe in the moment, but still there's some uncertainty there due to the wide range of parameters that you need to calibrate for these models, many uncertainty coming from the soil, and thus we can cast some doubt on where's the position of these dots into this plot, but still more or less, if we take the average, then they're kind of falling over the line. So at the end, we still have the same questions. We still don't know what the mechanics behind this hypothesis proposed by Musselman, but still it seems like the methodology is able to predict fractional strength. Thank you so much. Thanks for watching.